I may have to put up with those in order to record it, is what I have found. All right, what are we doing tonight?
Okay, so the things that we were working on, I just want to expand a little bit on that, because we went over the two triangles, and I've gotten that down pretty well, how to find the angles and all the trigonometry properties by using those. But there's just a couple of problems that within the chapter that I'm having problems on. So, okay, so for example, so like, okay, here's one. So it says, given a point on the terminal side of the angle, theta, in standard position is given, find the exact values. So the point that they give you is -7 and 2. I mean, -7 and -2. And then it says, find the cosine of theta.
Okay, now one thing I didn't talk about last time, and yet it is important to realize. There's a reason they call it the unit circle. Okay? And that is because if I look at this angle, I know that hypotenuse is 1, right? So if I create, what's that? Because it's the unit circle. In other words, that's why they have created this model of the unit circle, is so that they can make that hypotenuse 1. Okay? Now, if that hypotenuse is 1, what is the cosine of theta equal to?
Wait, but hold on. But so it's going to be 1 for every angle?
No, just it's 1 all the way around the unit circle. In other words, even if I draw the hypotenuse there, that has a length of 1 also.
Oh, if it's in the circle.
Right.
But, okay, but the other triangles that we did, they had like a hypotenuse of 2 and...
okay, once you get into polar coordinates, then it changes. You can increase the hypotenuse. But in terms of thinking about the unit circle, let's stay with the hypotenuse of 1. And it's important, and I'll show you why. What is the cosine of theta if the hypotenuse is 1?
It would be y.
No.
I mean x over.
That's it.
1.
That's it. And the sine of theta is y. Okay?
Yeah.
So that's the reason they use the unit circle. In other words, if I put 30 degrees there, then I know the x and y coordinate of that point. The x coordinate is going to be the cosine of 30 degrees, and the y coordinate is going to be the sine of 30 degrees. So and I kind of didn't talk about this last time, that when they want you to memorize the unit circle, what they generally want are those two things. And so it's important to understand that the x coordinate is cosine of theta, and the y coordinate is sine theta. Okay? So, if we go to this point here where it's not 1, but we can still draw a triangle.
Wait, so the x is sine or cosine?
No, x is cosine. Always.
X is cosine.
In the unit circle, x is cosine of theta, and y is sine of theta. Now watch what happens here before we get on to your problem. Watch what happens as we rotate this into the second quadrant. Let's make the angle 120 degrees. Okay, so this angle here is 120 degrees.
Okay.
Now, if I draw that, this is called a reference triangle. You probably have been taught this method. Okay, well, this angle here, notice that now the cosine of theta is going to be a negative x value. That's why the cosine is negative in the second quadrant, whereas sine, remember sine of theta is the y value, and the y value is positive right there. So sine of theta is positive in the second quadrant. And then as you go around into the quadrants, if you draw these reference triangles, you will see why it's ASTC. In other words, just looking at each of those reference triangles. The way I put it last week was I said, what is the equivalent first quadrant angle for all of these quadrants that are not in the first quadrant? That's the way I like to come up with the answer, is to convert them to a first quadrant angle. But that's in effect exactly the same as drawing these reference triangles.
Yeah.
Okay? In other words, this reference angle right here that I just drew, that is supplementary to 180 degrees, so it's 180 minus theta is how you come up with that. And that is the equivalent first quadrant angle. But it's also this thing they call a reference angle, which is the angle that measures to the x-axis, no matter which quadrant you're in. Okay? So, back to the problem of minus 7 minus 2. What do they want to know?
The cosine of theta.
Okay. So, here's the point. Well, let's draw the reference triangle. What's this measurement right here?
180.
No, the side of this triangle. In other words, I created what's called the reference triangle from this point. So that's x, right?
Yes.
And in this case, it's 7.
Isn't there like a 4, 5, 6, or like a 1, 2, 3,
There is.
4 or something?
The smallest one is 3, 4, 5.
Yeah.
The next smallest one is 5, 12, 13. So this is not one of those. Okay? But
how do you know
what we can tell about this triangle is that measurement is 2 and that measurement is 7, right?
Yeah.
I mean, we're on the...
Well, it's negative.
Well, it is negative, but you don't put measurement... Well, let's kind of separate whether it's positive or negative until we get to the end. It's always easy to figure out once you get to the end. I'm reluctant to put a negative sign there because that's not a dimension. You can't have a length of minus 7. What we have, in other words, if I'm talking about this triangle here, then a triangle has to have positive dimensions. Okay? It's true that the x goes in the negative direction and the y goes in the negative direction. So we can figure out what cosine and sine is going to be because we know that cosine is based on the x, so cosine is clearly going to be negative here, and sine is based on the y, so it's also going to be negative. Okay? What's the hypotenuse? In other words, you have to solve that triangle.
Right. Okay.
Solve this triangle.
So you square 2 and square 7, and so that's 4 and 49. And then you add that.
50.
No, wait.
That's correct. 53.
Yeah, you add it.
And then take the square root of it.
Yeah.
Okay. In other words, here's the underlying theorem. As long as you remember this, you can always figure it out. Okay? We were trying to solve for C, the hypotenuse. So C is the square root of A squared plus B squared. And that's what you did. You took the square root of 7 squared plus 2 squared. And notice that because I'm squaring them, it doesn't matter if they're negative or positive.
Okay. So yeah, I understand the Pythagorean theorem. I just didn't understand how to get the sides.
Yeah, this is not the unit circle. This is a point on the XY plane, and it's mainly a triangle problem. In other words, they could have said the exact same thing if they'd have said, here's a triangle, and this side is 2, and this side is 7. What's the hypotenuse? And then, once I came up with root 53, well, let's finish the problem. What's the cosine of theta equal to?
The cosine would be square root of 53 over... sorry. It'd be 7 over square root of 53.
Okay. And then is it a plus or minus?
Minus.
Right. And notice how we know. There's 2 ways we know. We don't really need our all students take calculus. Here, I'll tell you why we don't need that. We know that the x-coordinate is the cosine of theta. And we know that that's negative. I didn't put the negative on there because I was trying to dimension a triangle. But we certainly can see from that that that's negative. So that tells us that the cosine is negative. And the sine is also negative. What's the sine equal to?
It's 2 over square root of 53.
Okay. Now what do we have to do to both of those answers?
We have to multiply it by the square root of 53.
Top and bottom.
Yep.
In other words, you can't multiply the bottom by that unless you multiply the top by that.
Yeah.
Okay, and then that's going to give you minus 7 root 53 over 53. So there's the cosine. Yeah. This one's going to become minus 2 root 53 over 53. You always want to check and make sure you might be able to simplify that. In some cases, you can't here. But if that can be simplified, you definitely want to do it. But 53 is prime, so it's not going to be simplifiable. So when they give you a point in space, what they are really giving you is a triangle to solve. And as long as you know which quadrant it's in, actually, you don't need to do this. I didn't really need to do it this way. The moment you told me that point, I could draw a triangle. In other words, it might be easier to take this approach, which is, first of all, knowing that's third quadrant instantly. Okay? And now I'm going to just draw a triangle. And I know the cosine of theta is this side. I know the sine of theta is that side. Calculate that, square root of 53. And now I know what the cosine of theta is 2, or the sine of theta is 2 over that, and the cosine of theta is 2 over that. So I don't necessarily have to take the approach of the 4 quadrants and the reference triangle. But both work. Both give you the same answer. Notice why tangent is positive in the third quadrant. Because tangent's equal to sine over cosine. Tangent sine over cosine, and both of these are negative. So tangent is negative over negative. That's why it's positive.
So I have another problem because you know how last time with the triangles, I could find the tangents and all those easily because I knew all the sides based on what the rules for that triangle was.
Right.
On the test, in the chapter, there's going to be, there's a lot of other angle measures where you have to find out the cosine, sine, and tangent without using a calculator of the degrees. So, like, for example, cosine of 420.
Okay.
Oh, wait, no, sorry, not that one. I actually knew how to solve that one. Okay, cotangent of negative 9 pi over 2.
Okay. That is a multiple of 90 degrees.
Okay.
Okay. So this is one. In other words, anything that's a multiple of 30, 45, 60, or 90, we can do without a calculator.
Okay.
Okay. First thing to do.
Oh, this is of 90, so it'll make a 45-degree triangle?
No, it's actually going to be a 90-degree triangle. In other words, this is a quadrangle. Let's talk about the quadrangles for a moment before we talk about this. Okay? Because you can't get the quadrangle answers from, in fact, let me erase this. We do multiples of 30, 45, and 60, but from these two triangles, you can't figure out what 90 is. You can, but it's a little bit extreme thinking. Okay?
Yeah.
But you can figure out what 90 is if you look at 0. In other words, what is the cosine of 0 degrees? Well, what's the coordinates of this point?
Negative 1.
Positive 1, comma 0.
Oh, yeah, sorry, positive 1, 0.
Okay.
Yeah.
Let's look at this point up here. What are the coordinates of that point?
0, 1.
And over here?
That'd be negative 1, 0.
This is, to me, the easiest way to memorize it.
Yeah.
Okay. What did we say about the x coordinate? It's equal to what? Cosine or sine?
Cosine.
So the cosine of 0 degrees is this. The sine of 0 degrees is that. Okay, and let's go around the horn. What is the cosine of this point here corresponds to a 90-degree angle?
Yeah.
So the cosine of 90 degrees is what?
0.
And the sine of 90 degrees?
1.
Cosine of 180 degrees?
Negative 1, and then the sine is 0. Wait, but how did you know that it was going to be a multiple of 90 if it was 9 over 2 pi?
Well, because pi over 2 is equal to 90 degrees. Okay? Minus 9 pi over 2 is a multiple of pi over 2. It's 9 times pi over 2.
Oh, but it's negative, so would it be...
Well, let's go through that. Let's go through that. The problem was the cotangent of minus 9 pi over 2. There's two things we need to do first. We need to handle the negative sign, and to do that, we need to know if this is an odd or even function. Is cotangent odd or even?
It's odd.
Which means this is the same as minus cotangent of 9 pi over 2. That's step 1. Now let's take this angle 9 pi over 2. That is outside the unit circle. That is not within 0 to 2 pi. So it's coterminal, meaning it's some, we can take away multiples of 2 pi, or if you prefer, multiples of 360 degrees, until we get it inside the unit circle. Well, how many 2 pi's can I remove from that?
4.
Right. So I can subtract from this 8 pi over 2, which is 4 pi, and I get the same angle. So pi over 2 gives you all of the same trig function values as 9 pi over 2. So I can immediately substitute it by just removing. It's the same thing as if I said, okay, I have an angle of 730 degrees. Well, what's that in the unit circle?
Yeah, okay, I get it. So you'd have to see how many times 360 goes into it and then subtract.
It goes in twice. So I can remove two 360s, which is 720.
Right,
so that's the equivalent of 10 degrees. Okay?
Gotcha.
So that's the first thing you want to do, is turn it to a positive angle inside the unit circle. By the unit circle, I mean 0 to 360, or 0 to 2 pi. And that's what we've done here. So it's pi over 2 that we're talking about. So now the problem becomes minus cotangent of pi over 2. Well, let's go back to that drawing. Cotangent is what? What's the identity for cotangent?
Well, it's the inverse of tangent.
So what is it?
Hypotenuse.
Tangent is
adjacent over opposite.
It's more than that. It's the easiest way to do this is to know that the tangent is equal to sine over cosine, and the cotangent is equal to cosine over sine. Have you learned that yet?
No.
You haven't learned that? You'll learn that very soon. Okay?
Okay.
So cotangent is cosine of pi over 2 over sine of pi over 2. Now let's go back to that drawing I made. What's the cosine of pi over 2? This is pi over 2. This is pi. This is 3 pi over 2. And this is 2 pi, if you like.
Okay.
So let's read the pi over 2 is the angle we're talking about. What's its cosine? 0. And what's its sine? 1. So this becomes negative 0 divided by 1, or 0.
Yeah, okay.
Okay? Now,
wait, but do you multiply, if it was a different number other than 0 or 1, would you multiply it by pi over 2 on both top and bottom?
No, I'm sitting here trying to think if it was a different angle. Let's say it was pi over 4. Okay? Let's say after we did all of this. In fact, I can make it pi over 4 real easily. We'll just do that. Okay? There's our problem. Well, how many 2 pi's can I remove from that? All but pi over 4. In other words, I can remove 2 pi from that. So I'm going to turn that angle into pi over 4. So now if I want to figure out what's the cotangent of pi over 4, well, that's a little easier to do. It's not a quadrangle. A quadrangle is a multiple of 90. Cotan of pi over 4, well, let's figure out what the tan of pi over 4 is. What's the tan of pi over 4?
Well, it'd be, did you say sine over cosine?
Well, no, let's do it the normal way. Let's look at our 2 triangles and figure it out. In other words, the only time I have to use that identity is when we're dealing with quadrangles. If we're dealing with a regular angle, that is just a multiple of 30, 45, or 60, then I don't need to use those identities. So all I need to know is what the tangent is. The tangent is 1, so what's the cotangent?
1.
Right. So this would be -1. In other words, I didn't need to use the identity cosine over sine. I could figure out cotangent immediately. But figuring out these 3 secondary trig functions of quadrangles is a little trickier, I guess. Especially if we know our quadrangles from this picture here. In other words, if you're going to figure out all your quadrangles by doing this process that I showed you, where you look at the coordinates and that tells you your quadrangles, right? That only tells you them for sine and cosine. If I said, what is the tangent of 90 degrees? Well, you kind of have to know that the tangent is sine over cosine. So let's talk about that. What is the tangent of 90 degrees? What's the sine of 90?
It is 1 over 0. That'd be 0.
No. Look at that carefully. When you divide by 0, what do you get?
1.
No. You can't divide by 0. That's everybody's first commandment of mathematics is you cannot divide by 0. And when you divide by 0, you get undefined. What it really is infinity. It's the same thing as saying infinity. And in fact, if I draw the tangent graph, you've probably seen what the sine and cosine look like. But here's what the tangent graph looks like. It's got asymptotes on it. And it looks like this. Well, this is pi over 2. In other words, as you get close to 90 degrees, the tangent goes to infinity. This is minus pi over 2. As I get close to minus 90 degrees, the tangent goes to negative infinity. So it looks nothing like your sine and cosine curve. I mean, your sine and cosine curve look like this. There's the sine curve. The cosine curve looks like this. So what I normally tell people to do is memorize their quadrangles, multiples of 90 degrees, by memorizing these curves and knowing these quarter points. And then you'll have the curve or all your quadrangles memorized. But a student told me that he was taught this method in class, and I kind of like this method. Because this method here forces you to know that the x-coordinate is cosine of theta and the y-coordinate is sine of theta, as long as you're dealing in the unit circle. Now notice that that only applies if I'm dealing where everything's ones. That's why it's called the unit circle, and that's why they came up with it. Because it simplifies trig a little bit.
Yeah, but on the problem, it doesn't say whether it's like a unit circle problem. So
right. No, the unit circle is not so much for doing problems, but it's a great concept for figuring out these angles. In other words, there's a big advantage to having the hypotenuse be exactly 1. No matter what angle we're dealing with, that hypotenuse is 1 because the radius of all circles is the same. So every angle is going to have a hypotenuse of 1, which means the x-coordinate is cosine of theta and the y-coordinate is sine of theta, and that's useful to have a model like that. It makes understanding of trig a little bit easier. Now, that's not to say they're not going to give you problems like they did, where we have a point way out here that's at -7, -2. But that just means you have to draw a bigger triangle, and now our hypotenuse is square root of 53. Okay.
Okay. Okay, I think I understand. All right, so I have some more. Okay. So, for example, if it says to find the exact value of sine of theta if cosine is equal to 3/5 and the angle 270 is less than theta, which is less than 360 degrees.
So that additional information you gave me is we only need that for one purpose, and that tells us what quadrant it's in. So what quadrant is that?
That would be the fourth quadrant.
Okay, so I'm just going to write fourth quadrant. Okay. Now, all of these problems, you do exactly the same way. You don't draw the XY axis and put it in the fourth quadrant. You just draw a triangle. And you label one of the acute angles as theta. It doesn't matter which one you do. This is the way I always do it. Okay? In other words, that's the way you begin every type problem that is like this.
Wait, are you doing something on the board?
Now label this triangle for me.
Wait, are you doing something on the... Oh, okay, there, I see it. Sorry, I thought I didn't see it for a second.
There must be a delay. There must be a delay, because I had written that quite a bit earlier. Huh.
Really? Yeah.
Okay, but you see this triangle?
Yeah, I see it now. Okay.
So from this information, label that triangle as much as you can.
Okay, so...
What's this side down here?
Since it says 3/5, you have, adjacent will be 3, and then hypotenuse will be 5.
Okay. Now, that always allows you to dimension that third side.
Right. Oh, yeah, of course.
Because we have two sides. We have two sides of a right triangle. So what is this side? What was that Pythagorean triangle you mentioned earlier?
Right. So, I square 3 and square 5 and add them.
No.
So it would be 25.
No. This is the hypotenuse in this case.
Oh, yeah. Okay, sorry. I'm tired. Okay.
So this side is the square root of 5 squared minus 3 squared.
Yeah.
When you're solving for one of the sides, it's different. If you're solving for the hypotenuse, it's the square root of a squared plus b squared. But if you're solving for an a or a b, you have to square the hypotenuse first and then subtract the square of the other side.
Yeah.
But enough of that. What kind of triangle is this?
It's a 3, 4, 5 triangle.
Yeah. In other words, you should recognize this. You don't want to have to use the Pythagorean theorem to solve this.
Oh, okay.
Okay? When you see a 3 and a 5, you know this is 4. That's what I'm saying.
Okay.
If I gave you this triangle, 5, 13, you would know that's 12 instantly. Because these are your two smallest perfect Pythagorean right triangles.
Okay.
There's no 2, 3, 4 or 5, 7, 9 or any of that. 3, 4, 5 is the smallest one. 5, 12, 13 is the next smallest one. And these are used a lot. Not just in geometry, but in trig. So it's worth knowing these triangles. And just so you don't have to do the math every time when you're solving it. Okay?
Yeah.
So, now we have our triangle dimensioned. What do they want to know? The sine of theta?
The cosine.
Now, they gave you the cosine. They told you the cosine was 3
Oh yeah, sorry,
over
yeah,
5.
the sine. You're right.
Okay, so now read the sine of theta from our triangle.
It would be 4 over 5.
Okay, now we need a plus or minus because everything's positive there. So if I'm going to solve this problem with this kind of method, I'm not coming up with the plus or minus sign. I'm just coming up with the value.
Right.
So now I have to use the fact that it's fourth quadrant. What is the plus or minus sign in the fourth quadrant?
Negative.
Now I'm done. And using this method, it wouldn't have mattered whether they wanted to know sine. What if they had said, what's the tangent of theta? What's the tangent of theta equal to?
The tangent would be 3 over 5.
No. Opposite over adjacent.
Oh, yeah, sorry. Yeah.
So it would be 4/3.
4/3.
And what is its plus or minus sign in the fourth quadrant?
Negative.
Right. So, again, these are all positive numbers. And I just use positive numbers and triangles to get the number right. And you can always figure out the plus or minus sign based on its quadrant. Okay, so this method to me seems a whole lot easier than what they might teach. Here's what the way they might have taught it. I'm not going to spend a lot of time on it, but they might have said, here's the way to do it. And this point is 3, well, this would be 3, the hypotenuse would have to be 5, and then they would figure out 4, and then they would say the sine must be -4 over 5. So if you do it using reference triangles, then you don't really need to know all students take calculus, because you can figure out the sign. Notice why it's -4. And notice why it's +3. It's +3 because that's a measurement in that direction. It's -4 because that's a measurement in that direction.
Right.
But I prefer my method over this method. It's just that this may be...
I remember. I think that sounds familiar. I think that's what...
Okay, because some school systems really focus on this reference triangle method, and I really don't. I think that unnecessarily complicates it.
Yeah.
Especially for these kind of problems. These are the classical trig problem. If you could only ask one trig problem on a test, one only, it would be this one, or a variation of this one. Maybe they would tell you it's in the second quadrant, but they would tell you, and it doesn't have to be a nice smooth number. I'll give you another one. What if that is 3/8, and it's fourth quadrant? Now dimension the triangle. Notice how important it is to label theta. Because theta could be there or it could be up there, and it makes a huge difference on how I label this triangle. So you have to label some angle theta in order to be able to dimension it.
Right. Okay, so
that would be 3, that would be 8.
Yes.
What's that?
I don't know, so you'd have to square 8 and then square 3 and do 8 squared minus 3 squared.
So it's the square root of 64 minus 9.
9.
Square root of 55. So that's the square root of 55. Now that I have all 3 dimensions of the triangle, you can ask me about any trig function. I could ask you about any trig function. If I said, what's the cosecant of theta, you could tell me. Okay. And you'd be able to put its plus or minus sign based on the fact that it's in the fourth quadrant.
Yeah. Okay.
Okay?
Yeah, thank you. Okay, I get it a lot more now. Okay. So problems with radians, should I convert them into, okay, if it's a negative angle, how do I find
the best thing to do with negative angles is to use the odd or even property to get rid of the negative sign. In other words, if I had the sine of minus 10 degrees, I'm just going to immediately turn that into minus the sine of 10 degrees. If I have the cosine of minus, yes, these two are the same thing.
So what's the point of changing it?
Hold on. If I had the cosine of minus 20 degrees, that's actually equal to the cosine of 20 degrees, not minus the cosine of 20 degrees. That's a property of odd functions, and that's a property of even functions. Notice I've gotten rid of the negative angle in both problems. This is now a positive angle. Whatever I get for that, I'm going to put the negative sign there, but I don't have to worry about a negative angle. So every negative angle can be treated this way.
Oh, okay. So the angle is not going to be negative. It's just the sign of it is negative, the number of it.
Yes, exactly. There's a big difference between having that negative sign out front and having it in front of the degrees. And there isn't for sine. It's exactly the same for sine, but it's not that way for cosine. Notice. Cosine of minus 20 is the same as the cosine of 20. So the first thing you have to do is know whether the function is odd or even. And the only two that are odd are sine and tangent, and their reciprocals. And the only one that's even is cosine, and its reciprocal. Okay?
Yeah.
So that's how you handle negative angles. Now, in terms of handling radians, and as to whether you should convert to degrees or not, let me test you how good you are at converting degrees to radians and back and forth. How many radians is that?
Okay, so that would be, hold on.
Let's do it the hard way.
It'd be 30 pi over 180.
Well, when I say let's do it the hard way, you can do all of these forwards and backwards if you just use the conversion factor. Okay? The conversion factor is either 180 degrees per pi radians or pi radians per 180 degrees, depending on which way you're going. Okay? Which conversion factor do I need to use for 30 degrees?
Pi over radian. Pi
over 180. Because I'm trying to lose the degrees and pick up the radians.
So it'd be 6 pi.
Pi over 6.
Pi over 6.
Okay. In other words, if I do this the hard way, this way here is what I call the hard way, then that becomes 30 pi over 180, which becomes pi over 6. But remember what I taught you, that times that's always 180. So the quick way is to do it this way. Not this way, but the quick way is to figure out that that's, it's either pi over 3, pi over 6, or pi over 4, right? Well, it's got to be pi over 6. What's this one?
That would be pi over 45. 45 pi over 180 is it would be 4 pi over 4.
Okay. I have no problem with you doing it this method every time, multiplying it by its conversion factor. And that is certainly a way to do it. In other words, you have two choices, and that is to convert everything to degrees, always work in degrees, and if the teacher insists upon having the answer in radians, at the end of the problem, convert your answer to radians.
Right.
At some point in Trig, it's kind of like a foreign language. You're not going to want to have to do that all the time. You're going to want to be able to think in radians. In other words, when I say pi over 2, you don't want to have to convert that. You want to know that's 90 degrees. Always.
Yeah.
Okay? And when you reach that point, it'll actually be easier for you to do everything in radians and not go through that conversion back and forth. But that's kind of up to you. If you're not there yet, then it's fine to convert everything to degrees, work in degrees. Now, let me just test you. See, some of these can get a little difficult.
Right. Okay, so that would be, well, you would see how many times.
Well, I'm just going to multiply it by my conversion factor.
Okay, yeah, so it'd be 135 pi over 180.
Okay, now the difficulty is reducing that.
Yeah.
It turns out that 45 divides into top and bottom. The number 45.
45?
So that goes into there 3 times, goes into the bottom 4 times. So that's 3 pi over 4. But that's a lot of work. For you to do that, that's not that easy to do.
Yeah, and she doesn't let us use the calculator on this part.
See, I have gotten to a point where I know that's 3 pi over 4. I don't go through a conversion in my mind. I know that's 3 pi over 4. I know 150 degrees is 2 pi, it's 2 pi over 3. I know 120 degrees is, it's 120 degrees is 2 pi over 3. But in other words, once you get so you are kind of used to working in radians, you don't go through this conversion. And it makes it easier. It just makes it easier. It takes a long time, though. I mean, I've been tutoring this stuff for 7 years. So, of course, I'm going to know what 135 degrees is. So, but that's not that easy to memorize what all of your common angles are up to 360, you know.
Yeah. Okay, yeah, I mean...
We have another 10 minutes. We have another 10 minutes if you have some more problems you want to do.
Okay. Hold on. Okay, can we do some problems with central angle problems, like finding the length of the arc with radius 8 and central angle 210 degrees?
210?
Yes.
Okay. The length of the arc is that if it's in radians. But if it's in degrees, you have to convert it to radians. So if my angle is in degrees, which it is here, then I have to always multiply that by pi over 180. So there's the formula. Yeah, here, let me, well, no, you can think of it as being 2 different formulas. If it's in degrees, this is the formula. In fact, my book has 2 different formulas. One of them is this, the other is that, if it's in radians.
So does it matter?
Well, it matters on the answer, yeah. In other words, I could not use this formula for this problem because it's not in radians, it's in degrees. So I got to use this one. So my answer for this problem is 8 times 210 times pi over 180. There's the length of that arc.
Oh, okay.
Okay, and let me give you a little bit of a clue as to another way of thinking about this. They're talking about the length of that arc right there, right?
Mm-hmm.
Well, notice that if I want the length of the entire circumference, what would theta be? 360, which is what in radians?
Yeah, 360.
And what is that in radians?
It would be 2 pi.
Okay, so my circumference would be 2 pi r.
Yeah. Okay.
So that's a way to never forget it, because is all they're talking about when they talk about arc length is a piece of the circumference. In other words, when you're talking about an angle of 210 degrees, you're talking about the ray being over here. So they're talking about the distance from there to there, but that's just a piece of the circumference. But in order to memorize this formula, as long as you know the circumference is equal to 2 pi r from geometry class, you won't ever get it wrong.
Okay.
And it also kind of points out why it's easier to work in radians than degrees. Notice the formula for radians is much simpler. The formula for radians is just r theta. So if my radius is 8 and my angle is, say, 3 pi over 4, then 6 pi is my arc length. Don't have to do any conversion or anything. Yeah, in other words, it's much quicker to do that if your angle is in radians than it is to do that if your angle is in degrees.
So you always have to convert the degrees first to radians if you're finding
not necessarily. You can use this. In other words, the conversion of the degrees to radians is done by that right there, the pi over 180. And that's the only difference in the two formulas. So if your theta is in the degrees, you need to add a pi over 180 to the formula. If your theta is in radians, then you're all set to go.
Oh, okay. Gotcha. Okay. So, yeah, I think I pretty much covered all my questions.
Okay. Good.
Let's see if I have any last minute things to ask. Okay, so pretty much, if it's another angle that's not a multiple of 60, 30, or 45 or anything like that, and if you want to find the sine or the cosine or something, then you're
going to need a calculator. There's no way to do this without a calculator.
Oh, okay.
If I want the sine of 29 degrees, I don't know the dimensions on this triangle. I have no way to figure it out. But the calculator will tell me what it is.
Okay.
If I want the sine of 30 degrees, I can use my unit or my special triangle.
Right. So if it is a multiple, so if it's like 10, let's say.
Can't do it.
Sorry? Oh, can't do it.
Can't do it. Oh. I don't know how to figure out the sine of 10 degrees without a calculator.
Huh.
Now, if it's the sine of 22.5 degrees, you will probably learn half angle formulas and double angle formulas. And once you learn those, then you can do some odd angles that you wouldn't normally be able to do. Like I can do 75 degrees only because that's the sum of 30 plus 45, and there is a trig identity that tells me when I take the cosine of the sum of two angles, I can put my answer in terms of cosine and sine of those angles only. But you haven't gotten to that yet. So there are going to be some angles you'll be able to figure out without a calculator that are not multiples of 30, 45, or 90.
Okay, sorry, can I just do one more problem super quick?
Sure.
It's because I don't really understand this. So it says, use properties of trig to find the exact value, tangent of 10 degrees and cotangent of 10 degrees. And it's just right next to each other. I don't know if it means multiplying it, or I don't know what that means.
Oh, yeah. In other words, I don't need to know what 10 degrees, the tangent of 10 degrees is. What I need to know is that cotangent is the reciprocal. So this thing is equal to the tangent of 10 degrees, and in place of this, I'm going to write 1 over tangent of 10 degrees. And now I have tangent of 10 degrees divided by tangent of 10 degrees. That's 1.
Oh.
Okay. So we can do problems like this as long as we can get rid of the angle.
So even if they're different numbers?
Well, no, if it's different numbers, you're not going to be able to do it. Well, you might be able to.
Like if it's 10 and 20.
No, you wouldn't be able to do it. 10 and 80, maybe. But not 10 and 20. The reason I'm hesitating is because I don't think you've learned about cofunctions yet. In other words, the tangent of theta is always equal to the cotangent of 90 degrees minus theta. So I would say the tangent of 10 degrees is the same as the cotangent of 80 degrees, and that would be correct. But if you haven't learned that yet, then that's not going to be very helpful. So these kind of problems can be done as long as that's the same angle as that.
Okay. All right, then.
All right, Sonia.
All right. Thank you so much.
A good week. I'll talk to you next time.
All right. Thank you.
Bye-bye.
Thank you. Bye.